So next up, let's try an example of using the spring potential energy. So here's a simple example here. We've got a ceiling up at the top, and we have a block hanging from the ceiling, and it's hanging by a spring. Okay. Then we move this block to the rest length of the spring, and then we release it. And although the spring is not exerting any force at the rest length, this thing is hanging vertically, so gravity is going to pull it down, and what will happen in reality is you release it, it's going to bounce up and down. But this question is asking for how far will it go down before it momentarily stops and bounces back up again. See if we can figure that out based on the information in the question. So first thing we need to do, identify this is a conservation of energy problem. Identify what is the system we're studying. It's the block hanging from the ceiling. Identify what are the different types of energy that we're going to need to keep track of here. And in this case, we may need some kinetic energy because there's some motion happening in this problem. For kinetic energy, the formula is half mv squared. We have a spring here, so we should think about the spring energy, and the spring potential energy is 1/2 kx squared. And we also, this is happening vertically, so we're also going to want to think about the gravitational potential energy. So in this problem here, we may have to keep track of 3 types of energy. And remember, when it comes to energy, these are all just going to be added together to give you the total energy. So you just need to calculate them all and add them all up as scalars. Okay, next thing we need to do is identify what is the initial state, what is the final state. I've already drawn the initial state here. So at the initial state, the block is at rest, and it's at the rest length of the spring. I'll mark RL, rest length, okay? So it's at rest, at the rest length. Then we also need to sketch the final state. Let me do it over here. Okay, so there's my ceiling again. So this time the block will have fallen below where it was in the first picture. So the spring is more stretched out than it was. And the rest length is now up here. So it's dropped down below the rest length. And this is the point where it's momentarily stopped to change direction. So it's actually still at rest here. So maybe we actually don't need the kinetic energy in this problem because it's at rest in the initial state and it's at rest in the final state. It does have kinetic energy in between the initial state and the final state, but that's actually not so important because we're comparing the initial and final directly. Anyway, the other thing we need is to define a variable here. Let's call it x, which is going to be the distance between the rest length and the final length of the spring. Okay. All right. So now we've got a picture in our mind and on their paper of the initial and final states. The next thing is to start writing down the energies in the initial state and in the final state. For kinetic energy, we're going to have initial kinetic energy 0 because it's at rest. And over here, we're going to have final kinetic energy also 0 because it's at rest again. And again, it doesn't actually matter that the kinetic energy was non-zero in between those states. It just matters that it's 0 in the initial and 0 in the final. For the spring energy, this is going to be 0 in the initial state because x equals 0. In the final state, I guess I should call this US initial. In the final state, US final, it's not 0. It's going to be 1/2 kx squared. So half k is given in the question there as 10. I'm just not going to write the units to make my life a little bit easier. And then we've got x is my unknown variable. So the final spring energy is unknown, but it's going to be 5x squared. Not writing the units. Okay, then lastly, the gravitational energy. Remember, whenever you write down the gravitational energy, you need to be careful about making sure you know where your reference point is. I think I'm going to pick my h equals 0 reference level to be at the same place as the rest length of the spring, because that way x equals 0 and h equals 0 have the same meaning, which makes sense to me. So if that's the case, then my initial gravitational energy is 0 because it's at h equals 0. And the final gravitational energy is going to be negative, notice, because the block is below h equals 0. And it's below h equals 0 by an amount h equal minus x. So h equals minus x in this picture. Minus because it's below h equals 0, and x because that's the distance between h equals 0 and the current location. So I'm going to use mgh here. M is 0.5, g is 9.8, and h is negative x. So this is also unknown, but contains the same variable x as the spring energy. So this is going to be negative 4.9 x. Okay. Now, the next thing you want to do is add up to get the total energy in the initial state and the total energy in the final state. Let me do that here. I'm going to use E for total mechanical energy. So the total mechanical energy in the initial state is 0. The total mechanical energy in the final state is going to be 0 plus 5x squared minus 4.9x. Okay. Now I need to make a little bit of space. Let me just get rid of this picture so I have some room to work. Don't need any of this anymore. I just need my final result there. Okay. So the next thing I do is I set the total energy in the initial state equal to the total energy in the final state. That's the conservation of energy statement. So I'm going to have 0 equals, from down there, 5x squared minus 4.9x. I know that x equals 0 is not the solution that I'm looking for. So I can divide both sides of the equation by x, and it won't cause any problems. So now I'll have 0 equals 5x minus 4.9. Again, that was dividing the whole equation by x. And now I have a very simple equation. So I'll have x equals 4.9 over 5, which is just a bit less than 1. What is it, 0.98? Here's my calculator. Just double check that number. Yes, 0.98. And that's in meters because this was all in SI. Now, you'll notice that I got a positive answer. That's because I already included the negative sign to indicate that it was below h equals 0. That's built in to the equation that I wrote. So I was expecting a positive x because x is really the magnitude of the x vector, if you're thinking in that language. But anyway, so it's going to eventually bounce down to a point that's 0.98 meters below where I released it from.